Uh, Hello, thank you. My name is Denis Carnier. This is Type Inference Logics. This is joint work with François Pottier from Inria Paris and Stephen Keuchel from the Vrije Universiteit, Brussels in Belgium. So suppose you have a type system, and it looks like this. I thought my first slide should be inference rules. This is, after all, the type session. And you want to type check programs such as this one. And maybe you want to elaborate them, meaning you want to decorate them with explicit type annotations. How do you do this? Well, there's many approaches. If you want to do it in a principled way, then you should read this chapter in Advanced Topics and Programming Languages. If you don't have the time to read it, I'll just tell you what it says in a gross oversimplification. Basically, you take your input program, you generate a set of constraints, which you then solve, and then you use the sort of solved form to elaborate to an equivalent program with explicit annotations. I'll walk you through a worked example now. This is the definition of Boolean negation. So Boolean negation is a function. It takes an x, and if x is true, then it returns false, and if it's false, then it returns true. So you existentially quantify over any of the unknown types, and then you simply traverse the program, meaning you equate alpha to a function type from beta to gamma. Then you look at the body of the function, you equate beta to booleans, and then for each of the branches in the if expression, you equate those to the unknown existentially quantified gamma. Then you solve them. I'm going to skip over this, but there's many techniques to solve them. And you arrive at a kind of canonical solved form. You apply this to the original program, and you arrive at the equivalent program now with explicit binders. Some people call this zonking. I simply call it applying the substitution. So constraints are great because they give you a clear interface that sort of tells you between the two phases, between constraint generation and solving, what should happen. There's an intuitive semantics there. You get separation of concerns. You can now simply traverse the program and turn a big source language into a small constraint language. But what about type inference in the real world? Does it use this style of constraint-based type inference? Well, it turns out Glasskull uses this, and they've spent a lot of PhD students trying to figure out the best way to do type inference. So I'll just walk you through what the GHC does. It takes a source expression here, an expected type, and then it has this type checking monad to return an elaborated expression. And this is really what we've been doing now. So this is the if case we're looking at. We're equating sort of the predicate to be a Boolean, just like before, and then we say that the two branches should equate to bools. So this paper's question is, how do we reason about these kinds of type inference algorithms, where we have constraints and we need to reason about scoping, particularly about existentially quantified type variables. There's effectful programming happening. There's state and option. There's abstractions. We're using monads. We need to elaborate to explicitly typed programs, and we have these multiple phases going on. I'll try to give you a friendly overview, and if there's some time, I'll show you the nitty-gritty details. So we're going to combine a couple ideas. Maybe some of you have read this paper. This is by François Pottier in 2014. It's a functional Perl, where he comes up with this kind of idea which he calls constraints with semantic values, which is to say it's a kind of type that at the same time is a constraint that should hold, and also it would yield a program of, it would yield a value of type A if the constraints hold. And also, importantly, the value of type A can depend on the solution of the constraints. So practically for us, this allows expressing both that the type constraints from the source, that the typing constraints from the source, I'll redo that. So for us, this would mean that we can do one traversal where we both generate the constraints of the program and at the same time can already specify what the elaborated program will look like. So let's use that to define a monad interface for constraint generation. So we define some operations like pure, which allows, essentially it's a truthful constraint, so a trivial constraint that holds and just injects a value into the monad. We use bind as a way to model conjunction. We have failure in case a program is ill-typed. And then we have type equality and pick. And the type signature for pick looks kind of funny. It kind of just magically comes up with an object language type. More on this later. Can we define a constraint generator with this interface? Let's try, yeah. So here's a function called synth, which takes a typing environment and an input program and matches on it. Importantly, the output type is sort of this monadic values. This will be a constraint and the value that we should return is a product of a type and an elaborated expression. Let's just look at the lambda case here. So we magically come up with a type. Let's call it tau1. And then we extend the typing environment with binding for x to tau1 and type the body of the lambda. And then return in the pure function type from tau1 to tau2 and an elaborated program that now has x explicitly bound to or explicitly typed as tau1. The question is, can we implement m? So is there a sort of instance for this monad interface that we picked earlier? Well, there's a kind of standard construction called the free monad instance, where essentially you don't define any semantics for the monad operations, but you simply come with a data type that has constructors for each of the operations in the monad. So each of the constructors carries the input. In this case, for example, pure carries the input A. And then there's a continuation, which we omit if it's just trivial. The equality takes, for example, 2 taus, so 2 object language types, and the continuation is just more constraints. And the pick operator uses this kind of function space from the meta language to sort of come up with a continuation that takes a tie. This is also kind of magical. I will get back to this. So now we've defined synth, and the question is, can we prove that synth sort of overlaps with our declarative type system? So the second idea that we'll use is something called domain-specific reasoning. There's this nice quote from a beautiful paper by Nigon and Dagan, where they say that every monad deserves its own Hoare logic, essentially. And we're going to use this to kind of define a denotation of constraints. So essentially, we define this funny-looking function called WP, which is essentially program logic for constraints. So given a constraint of type free A, and a postcondition that takes an A to a proposition, we can define what that means, essentially. The important case here is the pick case, where we essentially use the meta-language propositions to existentially quantify type, and then, we existentially quantify it in such a way that the constraint will hold. So this is kind of like an angelic choice, if you're familiar with program logics. If you're having trouble sort of getting an intuition for this stuff, you can ask a program logic expert, and they will say something like, if you have the WP of some constraint and a postcondition, then what this really means is that there exists a value such that the constraints that the constraint can produce for which the postcondition holds. So equally, you can say that the constraint can satisfy the postcondition. Using this, we can now define an algorithmic typing relation. Algorithmic with scary quotes, because it's still essentially a non-deterministic program. And then we can define what that means. Essentially, we can say that there's, so the algorithmic typing relation is now defined as being able to produce the pair of tau and E prime. We now have the correctness from before, which we can now state as a bi-equivalence or a bi-implication from the algorithmic to the declarative typing. This boils down into 2 directions, which are commonly called soundness and completeness. Maybe we'll look at completeness first. So this says, given a typing derivation, we should be able to get an output of the inference algorithm. And then the goal here is just in a standard program logic style, or the standard deductive verification style, construct such a WP statement using the program logic rules from before. Soundness is a little bit more tricky. Essentially, we have to destruct this WP statement because the algorithmic typing is now an assumption. So maybe we can try something else. We can define a dual semantics. So recall we had WP before. We can now define WLP, where we essentially allow failure. So this is liberal in the sense that failure in the constraint is allowed. And we flipped what were previously conjunctions in the E case to implications, and an existential quantifier into a universal quantifier. And what this allows us to do is essentially rewrite statements of the form WPCP, so maybe we should put parentheses here, implies Q, into WLP statements. And so recall that WP meant that some execution of C satisfies P, and now WLP will say that all executions of C satisfy the postcondition. And then there's this theorem, which you can prove by induction on C, that these 2 overlap. This is not true in general, but it is for our semantics. And now soundness can be rewritten not as destructing the WP, but instead constructing a WLP according to this dual semantics. So you can use program logical rules here as well. That was the friendly overview of doing soundness and completeness for this kind of stuff. I'll give you, in a lightning round, what the rest of the paper was about. So you've now learned the first 2 pages of our paper. So it turns out using this function space of the meta language for modeling the pick operator is kind of cheating, because you're using a higher order abstract syntax to sort of hide the freshness and hide the scoping of existential variables. So instead, we do what a lot of people do nowadays, which is use Kripke indexing. So we have worlds where we explicitly track the variables that are in scope, and then we restrict types which are now indexed by a world to only be allowed to index those type variables that are in scope. And now we redefine the sort of the free data types, so the constraints, using this explicit notation for bound variables. So they're now essentially a family of types. So a family in the sense that for every world you can define such a type. And then with some handy notations to hide a lot of the world indexing, we redefine a bunch of the stuff that we did earlier. So here's now a new monad interface. You might see that box in the... Oh, it works again. Okay. Yeah, thanks. So we redefined the monad interface, and now we are working with this kind of explicit substitutions everywhere. We redefined the constraint generator again. This thing keeps cutting out. It's kind of annoying. Yeah, thank you. So we also have constraint solving here, and then we have this run function, which essentially takes a program, sort of a constraint, turns it into pre-next form, then tries to solve it. I'm going to skip over some of this. Essentially, instead of using propositions in the meta logic, we now index them by assignments, which is to say a kind of ground link substitution to all unification variables to monotypes. And we use this as additional knowledge in the proofs. Essentially, we can sort of pretend that we already have a solution and track that there. We lift all the logical connectives to this new assignment index, and then we can restate correctness in terms of this logic. We mechanize all this in Coq, just for fun, I guess. We split it into 2 categories. So there's this generic category and the specific one. We looked at lambda bool. We're hopefully going to generalize this to a number of type systems. But the spec to proof ratio is pretty good. I don't know if you've done mechanized proofs in Coq before, but typically you don't get close to 1-to-1 ratio, so that's pretty neat. And then we also did code extraction to Haskell for our tiny type inference algorithm with a toy parser and pretty printer. And then there's a bunch of stuff that I didn't talk about. So there's another proof method with using logical relations, or Kripke indexed logical relation. We used Iris for proof automation. There's constraint solving, and then various interesting type systems that we still should extend to. That was my talk. Thank you.
Thank you, Denis. Are there any questions? Then please step up to the microphone there.
Whoa. Yeah, really great talk. Thanks so much.
Thank you.
I think I was following along with the math for a while, and then suddenly modalities appeared kind of out of nowhere. Could you please motivate that and, yeah, kind of explain where that came from?
Yeah. So essentially I wanted to make 2 talks, and I chose to give one, which was the high-level overview talk. But there's another talk that I can give to you maybe offline if you're interested, Essentially, sort of what I shoved under the rug for the first 10 minutes is this this scoping of existential variables. So essentially here in this definition, for the constructor of pick, I'm using higher order abstract syntax to hide away sort of the binding of an existential variable. And so the rest of the paper, which is the part that I swept under the rug, is making this actually explicit and tracking this because it's quite important to the proof correctness. You want the scoping to be correct. And then essentially, once you're working with this sort of monotonic state, a very nice way to reason about it is using these Kripke is to use Kripke indexing and have a bunch of these modalities. I don't have the slides that show the modalities here, but maybe offline I can show them to you, and we can talk about it. Thank you.
Yeah, great. Thanks.
Hello.
Hi.
Thank you so much for the talk. So on the earlier slide, when you first introduced the type-checking monad, I was wondering what the pick does. I don't think I'm fully on top of that, because other things I kind of understand that it's just a normal monad, but what does the pick do, and why is it there, and why does it have to be there?
Yeah, that's a really good question. So essentially, we're defining an interface here, and it's not clear whether there's actually an implementation of this interface. And because it's not clear, we can essentially do whatever we want. We can have an operation that sort of magically comes up with a type, which is what this operation does. And we're sort of thinking about ways to implement this interface later on. So the intuition for the pick operator here is basically what I just said. So you can just think of it as magically come up with a type.
Okay. So would all of the instances of like these kind of monads have this pick, and like, so why is it implemented? I'm more like confused of like what's the incentive of having this operator in this interface?
I can show you the constraint generator again. Maybe I'll show you slide 1. Maybe you look at the bottom left type inference, the bottom left rule here. So this is a typing rule for lambda abstraction. And it says that you can conclude basically in the bottom, lambda x.e admits this function type from tau1 to tau2, provided that you can type the body of the lambda e in a context that's extended with a binding for x to tau1. And what this is really saying is we need to somehow come up with tau1. And then this operator in the monad is in particular allows you, if I can find it, to magically come up with this. So if you then look at the implementation for synth, sort of the first line of the lambda abstraction is saying magically come up with a type.
Okay. Yeah, that makes sense. Thank
Cool.
you. Cool. I do have a quick question, maybe.
Sure.
Which is you said that the coq code and the specification were actually pretty close in number, which is pretty impressive. Do you have any sort of intuition for why that is?
Yeah, so we're very careful to sort of keep automation very high. That is to say, we hide a lot of what you would normally do, which is explicit reasoning about substitutions. We hide this under the modality stuff that I will talk to the gentleman from the first question about. And then essentially what we did is we instantiated this coq library called Iris, which is essentially a library that implements a separation logic, also called Iris. But importantly, what they do is they have this this proof mode that allows you to sort of reason with modalities, introduce them and eliminate them very easily with a lot of proof automation, which is also what we did. But this is not a separation logic. Thank you.